Hello everyone, welcome back. Let's talk about another easy problem on Leetcode today, counting bits, Leetcode 338. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an integer n and our task is to return an array answer of length n plus 1 where answer I is a number of ones in the binary representation of integer I, where I is a non-negative integer from 0 to n. Then in example 1, for n equal to 2, we need to compute the number of set bits, that is, bits with value 1 for all the numbers from 0 to 2, and binary representation of 0 is 0. So number of set bits here is equal to 0. Next, binary representation of 1 is 1. Of course, all the other preceding bits are 0. So number of set bits in 1 is equal to 1. Then binary representation of 2 is 1, 0 with only one bit set. And hence we will return the array 0, 1, 1 as our answer. Now in terms of solution, one of the naive approach can be to iterate through all the integers from 0 to n and determine the number of ones in binary representation of each integer. And to get number of set bits in an integer, we can use any method that we have already covered in the problem, number of 1 bits. If you haven't already, I highly recommend checking out the video in the I button or in the description below for more detailed explanation on the topic. Here I will cover this topic briefly. There are multiple ways to get number of set bits in an integer. One way can be, we can use standard or built-in library functions. For example, integer.bitCount in Java or built-in bin function in Python. Another approach can be that we can use Bryan-Kernighan's algorithm, or the simplest method is by doing division by 2. The idea is simple. When we divide a number by 2, the remainder indicates whether the least significant bit is set or not. If the remainder is 1, that means the bit is set, so we increment our bit count. For example, if we take the number 5, dividing it by 2 leaves a remainder 1. That means the LSB in this number is set, so we increment the bit count for this number by 1 and perform the integer division, which will result in number 2. Now we again divide the number by 2, which leaves no remainder. So that indicates that the least significant bit in this number is not set, and hence the bit count stays 1, and we again perform the integer division by 2. And this time we will get the number as 1, and now dividing the number by 2 leaves a remainder 1. So the bit count becomes 2, and finally once we perform the integer division with 2, we will get 0. So that means we are done with this number, and hence number of bit counts in this number is equal to 2. So this process is repeated for every integer from 0 to n. The time complexity of this approach is O of n log 2n, because first we iterate through all the numbers from 0 to n, and then for each number counting the set bits takes log of 2n time in the worst case, because at each step we are dividing the number by 2. Hence, the overall time complexity for each integer is log 2n in the worst case, and hence the overall time complexity will be O of n into log 2n, and the space complexity of this approach will be O of n for using the answer array to store the results, which we need anyways. So the auxiliary space complexity will be O of 1. Now let's see how we can improve over the naive solution. The issue with the naive approach is that it performs repetitive work for every number from 0 to n, recalculating the set bits for each number independently. By identifying patterns in how bits in binary representation change, we can eliminate redundancy and streamline the process. For example, one such pattern is that of powers of 2, with numbers like 1, 2, 4, 8, 16 and so on. These numbers have exactly one set bit in their binary representation. And this is because the numbers can be expressed as 2 to the power of m, where only one bit at mth position is set. But what about other numbers? For numbers other than powers of 2, their binary representation follows a predictable pattern. Any number I can be written as 2 to the power of m plus r, where 2 to the power of m is the largest power of 2 less than or equal to I, and r is the remainder obtained from subtracting the power of 2. For example, number 5 can be written as 2 to the power of 2 plus 1. The remainder r represents how many bits differ between I and the nearest power of 2. By observing the structure of I, we see that number of set bits in integer I is equal to 1 plus number of set bits in R, because power of 2 only has one set bit. To illustrate this, we can draw a table of numbers up to 10. So in the table, we have numbers, their binary representations, and number of set bits in them. So 0 is the base case and it has 0 bit set. Then we see 1, it has 1 set bit. Then for 2, the binary representation is 1 0 and it has 1 bit set. And both numbers 1 and 2 are power of 2, and hence the remainder R is equal to 0. So we can write number of set bits in integer 1 as 1 plus number of set bits in 0, and the number of set bits in 0 is 0, which we have already calculated at index 0 as the base case. Similarly, for number 2, as the remainder is 0, we can calculate the number of set bits as 1 plus number of set bits and remainder 0, which is equal to 1. So now let's see how we can apply the remainder technique that we just discussed to count the number of set bits apart from power of 2. So then the next number we see is 3, which has 2 bit set, which is equal to 1 plus 1 coming from the power of 2 plus number of set bits in remainder 1, which is equal to 1, and hence total number of set bits in 3 is 2. So for the numbers covered in the table, answer for number 1 was 1 plus answer for remainder 0, which we can rewrite as 1 plus answer 1 minus 1. Similarly, answer for number 2 can be written as 1 plus answer for remainder 0, which we can rewrite as 1 plus answer of 2 minus 2. Similarly, answer for number 3 is 1 plus answer for remainder 1, which we can rewrite as 1 plus answer of 3 minus 2. So if we continue down this line, this follows a recurring pattern that resembles following recurrence relation, where answer for number I is equal to 1 plus answer for number I minus maximum power of 2 we have seen so far. And this second term represents the remainder when subtracting the nearest power of 2 from I. So at its core, this is the idea of the dynamic programming, where the solution to a larger problem is constructed using solutions to smaller subproblems that have already been solved. Specifically, we can express the recurrence relation as dp of I is equal to 1 plus dp of I minus offset, where offset is the largest power of 2 less than or equal to I. This formula allows us to incrementally build the results efficiently, avoiding redundant computations. So coming back to the table, for number I equal to 3, we can calculate number of set bits as 1 plus dp of I minus 2 equal to 2. This bit is coming from power of 2 and this bit is coming from the remainder, which we get from dp of I minus 2. Now we see 4, it is power of 2. Hence it will have 1 bit set, which will be equal to 1 plus dp of I minus 4, as 4 being power of 2, this is the new offset, which is equal to 1 plus 0 equal to 1. Then the next number we see is 5, and number of set bits will be equal to 1 plus dp of I minus 4 as well, which is equal to 1 plus dp of 1 equal to 2. Then the next number we see is 6, which will be 1 plus dp of I minus 4 equal to 1 plus dp of 2 equal to 2. Then the next number we see is 7, and the number of set bits in it is equal to 1 plus dp of I minus 4 equal to 1 plus dp of 3 equal to 3. Then we see 8, which is a power of 2. So it will have only one set bit, which we can write as 1 plus dp of I minus 8. Now the offset is 8 till we see next power of 2. Then we see 9, which is 1 plus dp of I minus 8 equal to 1 plus dp of 1 equal to 2. And then we see number 10, and number of set bits in it is equal to 1 plus dp of I minus 8 equal to 1 plus dp of 2 equal to 2 as well. So using this insight, we can iterate through numbers from 1 to n and compute the count of set bits for each number using the recurrence formula. Now the time complexity of this approach is O of n, because this algorithm iterates through numbers from 1 to n, performing a constant time calculation for each number based on the recurrence relation. And the space complexity will be O of n as well, because we are using the DP array of size n plus 1 to store the set bit counts. But the auxiliary space complexity will be O of 1, because anyways we have to return this DP array as our answer. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on the left and Python on right. First, let's create DP array or list of size n plus 1 filled with all zeros, and dp0 is the base case. Now let's initialize the offset to 1. This offset represents the largest power of 2 encountered so far. Now we will iterate through all the numbers from 1 to n. Now if the number I is equal to power of 2, that is offset into 2 is equal to I, then we will double the offset or set offset equal to I. And now number of set bits can be calculated using the recurrence relation, which is dp of I is equal to dp of I minus offset plus 1. And once we are done with all the elements, we will return dp array as our answer. Now, continuing from the previous dp approach, we can refine the solution further by focusing solely on the division of the number by 2. This way, unlike the previous approach, there is no need to explicitly track power of 2. Let's take two numbers x and y such that x by 2 is equal to y, which we can also write as x right shift 1 when using the bitwise operation. So now let's take these two numbers x and y and see if we can reduce number of bits in x from y. Now when we divide the number x by 2, there are two main cases to consider, which are whether x is even or odd. First, let's look at the case when x is even. In this case, its least significant bit is set. So dividing x by 2 or right shifting it gives y, which has the same number of set bits as x. For example, let's take x equal to 6 with binary representation 110. And now if we divide this number by 2, we will get y equal to 3, which has binary representation of 011. As you can see, both 6 and 3 have same number of set bits, which is 2 in this case. Now let's take case 2 where x is odd. For example, x is equal to 7, and when we divide 7 by 2, we will get y equal to 3. Now when x is odd, its least significant bit is 1, and dividing x by 2 gives y, and the number of set bits in x is then 1 more than that in y. For example, binary representation of 7 is 111 and that of y is 011. So when we right shift 7 by 1, this bit is removed and hence we get y equal to 3 with 2 set bits. So in this case, number of set bits in 7 is equal to 1 plus number of set bits in 3. So from these cases, we can define our recurrence relation as dp of I is equal to dp of I by 2 plus I mod 2. This correctly accounts for number of set bits in I by dividing I by 2. This way, we reuse the result of smaller subproblem, which we would have already solved for number I by 2. And if I is odd, I modulo 2 will leave the remainder 1. So, we add 1 to the result as the least significant bit is set. Alternatively, as we discussed in the number of 1 bits problem, we can express this completely with the binary operators, where we can replace I by 2 with I right shift 1 and I modulo 2 can be replaced with bitwise AND operation between I and mask 1. And now that we have established the recurrence relation, we start with the base case where dp0 is equal to 0 as number 0 does not have any set bits, and then we iterate from numbers 1 to n, filling in the dp table using the recurrence relation in a bottom-up manner. This approach reuses previously computed results, ensuring efficiency while avoiding redundant calculations. And once we have filled in the dp table, we will return it as our answer. And the time complexity of this approach stays O of n as we loop through the array from 1 to n, and both bitwise AND and right shift operators take O of 1 time for each number. And the space complexity of this approach will be O of n as we require answer array to store the results. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.